You know, it's kind of funny. We always think of power and force as things that move, a speeding car, a crashing wave. But what if I told you that some of the most incredible forces on Earth are found in stuff that's not moving at all? That's right, we're talking about the hidden power of still water. So, let's kick things off with a little puzzle. Just look at this dam. It's holding back an entire lake, but the water isn't crashing against it, right? It's just sitting there. So how in the world can quiet, perfectly still water push hard enough to challenge a wall made of solid concrete? That's the mystery we're going to unravel today. Well, the answer is all wrapped up in a field of science called fluid statics. And hey, don't let the name fool you. If it sounds a little too much like a textbook, just think of it as the science of stillness for anything that flows. You see, before we can even begin to understand fluids in motion, we have to nail down what they're doing when they're just chilling. It's the absolute foundation for everything else. Okay, so first things first. What even is a fluid? Well, the simple answer is, it's anything that flows. And that means this isn't just about water in a dam or the ocean. Nope, it's also the air we're breathing right now, the natural gas in a pipeline, even the plasma inside a star. Now, for what we're doing today, we're going to focus mostly on liquids, but just remember, these principles apply across the board. And here's where things get really cool. This is our first major shortcut. When a fluid isn't moving, all the messy, complicated forces like friction between the different layers of the fluid, they just disappear. It's kind of like a deck of cards, right? When you slide the top card off, you feel that friction. But when the deck is just sitting there still, no friction. It's the same with a still fluid. All those other forces just go away, and we're left with one single, all-important force: pressure. So if we want to crack the code of that dam, we first have to get a really good handle on pressure itself. I mean, it's a word we throw around all the time, right? Tire pressure, blood pressure, weather reports talking about atmospheric pressure, but what is it really? Okay, so at its very core, pressure is just force, but it's force that's spread out over an area. Think about it like this. Imagine pushing on a wall with the flat of your hand. Now imagine pushing with that same exact force, but only using the tip of your finger. Ouch, right? Same force, but because you're concentrating it on a much tinier area, the pressure goes way, way up. It's all about how concentrated that push is. All right, now here's the first rule about pressure that might bend your brain a little. If you could shrink down into a tiny submarine and hang out inside a glass of water, you wouldn't just feel the pressure pushing down on you from above. No way. You'd feel it squeezing you equally from every single direction at once. From the top, the bottom, the sides, all of it. Pressure doesn't have a direction. It's just this all-encompassing squeeze. And the second rule is something I bet you've actually felt. You know when you dive down to the bottom of a deep swimming pool, and you get that feeling in your ears? That's pressure. The deeper you go, the more water is literally stacked up on top of you, pushing down. And here's the key. This relationship is perfectly linear. You go twice as deep, you get twice the pressure. Simple as that. Okay, so we've got two simple rules. Pressure pushes everywhere, and it gets stronger the deeper you go. With just those two ideas, we can build some unbelievably powerful machines. In fact, they help us solve a really common puzzle that you've probably experienced every day without even thinking about it. I mean, really think about this. How can a simple push of your foot on a pedal bring a 2-ton car to a screeching halt? It seems impossible, doesn't it? The little bit of force from your leg versus all the momentum of a giant metal box? The secret, my friends, isn't magic. It's hydraulic fluid and an absolutely brilliant principle called Pascal's Law. So Pascal's Law is the solution, and it's actually pretty simple. It basically says this: if you have a fluid in a sealed container, think about your car's brake lines, and you increase the pressure in one spot, that exact same pressure increase happens instantly, everywhere else in the fluid. It's like a perfect little messaging system. A push over here is felt exactly the same way over there, at the exact same moment. And this is how that simple law becomes this incredible force multiplier. Here's how it works. Your foot applies a small force on a small piston at the pedal. This creates pressure in the fluid. Now, that same pressure travels all through the brake lines to the wheels, where it pushes on brake pads that have much, much larger pistons. So you have the same pressure acting on a bigger area. And what does that equal? A massively multiplied force. It's just simple physics that lets your little foot command 2 tons of steel. Amazing. All right, so we've cracked the code on the car brakes. Now we have all the tools we need to go back to our first and much, much bigger puzzle, that massive dam holding back an entire lake. And here it is, the answer to our big mystery. The force pushing on that dam isn't the same everywhere. Remember how pressure increases with depth? Well, that means the push from the water at the very bottom of the dam is absolutely immense compared to the gentle little push at the surface. And that is why dams are always engineered to be so much thicker and stronger at the base, because that's where the real battle is being fought.
And you know what? That same principle, that upward pressure from the deep water, that's what gives us buoyancy. Think about a giant ship or a massive iceberg. The pressure pushing up on the bottom of it is way greater than the pressure pushing down on the top. The result? A net upward force that lets these huge things float. It's all the same physics at work, whether it's holding back a lake or holding up a cruise ship. And once you start looking for it, you see these principles literally everywhere. Understanding fluid statics is absolutely critical for designing dams and storage tanks, obviously, but it's also key for naval architecture, building ships and submarines. It's the basis for all hydraulic machines, like the lifts in a mechanic's garage. It's used in complex pipeline networks, in medical devices that have to measure blood flow, and yeah, even in the early design stages for aircraft and rockets. It's fundamental.
Okay, so we have spent all this time talking about stillness, about perfect balance. But what happens when that balance gets broken? What happens when the forces don't add up to zero anymore? Well, that's when we leave the calm world of statics and jump headfirst into the other half of mechanics, dynamics. In statics, everything is in balance. All the forces cancel each other out, so the net force is zero. But in dynamics, the forces are unbalanced, and that's what causes things to speed up, slow down, or change direction, all governed by Newton's most famous law: force equals mass times acceleration. It's not the science of stillness anymore, it's the science of motion. So, when a fluid isn't still anymore, like the air flowing over this race car, the forces at play are about a lot more than just static pressure. Suddenly, you get these new, powerful forces like lift and drag that come into the picture. The science of stillness gives way to the science of motion. And trust me, that's where things get really interesting. So we've unlocked the secrets of still fluids, the silent power that lets us build these incredible structures that hold back entire lakes. But mastering stillness is really only half the story. So the final question to leave you with is this: what happens when we take these same fundamental ideas about force and pressure and we use them not to prevent motion, but to predict it, to control it, and to design incredible things with it? Well, that's the story for another time.